Antonio from the Glotzer group in chemical engineering. He will be talking about dynamic self-assembly. And so, thank you.
Good morning. Hi, I'm Antonio Osorio, and I'll be talking to you about, like Paulo said, about dynamic self-assembly of colloids. So, basically, as we try to make new materials and design new devices, we're trying to make the features of those materials as small as possible. And the way that we've done that so far with computers and chips is by having like a planar techniques that let us build the features from the top down, where we design all the little features, all the different patterns in the material, and then we transfer that onto the material itself, and then we see the properties that they come out. As we advance and we try to do more and more complex things, try to get new structures, try to get new materials with properties that we haven't seen before, this becomes increasingly difficult. An approach to go to making these new materials is self-assembly, where we design the building block. So, like in complex systems, we decide the local interactions, or how that little unit is going to work, and how is it going to interact with each other to be able to have a property on the block when they assemble together. Some of the things that we have tried so far is to change the shape of the building block, make it into spheres, into squares and crosses and all different kinds of shapes. We've tried adding different patches that have different interactions between them, hydrophobic, hydrophilic. So we always try to change how these particles behave on a local level with the hope of affecting how they will behave in the bulk. So you see some emerging properties from those particles, right? In our group, Pablo did a very large study of all like a bunch of different polyhedra and what they could assemble if you just by high interaction, just by as a function of shape, you just put them together in a bucket, shake the bucket, and let it come down to the densest packet. And we can see that with just these simple interactions, with these simple rules at the building block, we can create different crystals, we can create plastic crystals, liquid crystals, and disordered structures. So we already see ordering from these rules. But so far, all these changes to the particles have been static. So you design your particle, you give them some properties, some interactions, and then you let it assemble to its equilibrium configuration. So you just let it sit, let it go to wherever it wants to go, and then there is no control after that of what the particle, what the resulting structure is going to be. What my work does is to actually try to add some temporal dependency to those systems. And this leads us to dynamic self-assembly, where the building blocks, where the rules of the system are still defined as the building blocks, but they are changing as a function of time. Or at least they are changing to adapt to their environment. Some examples of this is like how the cytoskeleton in the cells grows and starts destroying itself to match the shape of the container. How like colony of bacteria grow to adapt for different food sources, and the school of fish travel together to scare predators and again they all don't have like a guiding force that is putting them all the pieces together. They all just know individually what they have to do, and by they all following their local rules, they can form something more meaningful. You know, where the whole is more than the parts of the system, right? And as our ability to synthesize new materials, new building blocks evolves, we're able to build these temporal dependencies, these switching interactions into our building blocks for making new materials. And I'm going to talk about two systems that I've been working on. The first one is a very simple system. It has two types of particles, and these both are our simulation experiments. So we have two types of particles. Imagine like the blue particle and the yellow particle. They are kind of like water and oil, where if you mix them together, the water molecules or blue molecules want to be with other water molecules, and the yellow molecules, in this case the oil, would also like to be together. So if you just create these two building blocks, put them together, let them organize as they see fit to find their minimum energy configuration, their stable configuration, they just separate into two regions. One full of yellow particles, another one full of blue particles. But then we go ahead and throw a range onto the system. We let a particle of one type switch to the opposite type at random. So there is a probability of switching from one type to another, and this frustrates their ability to phase separate, because now these particles are constantly switching to the opposite type and trying to diffuse to go back into those regions, but the constant switching is not going to let them. I mean, not to spoil the ending, but one of the resulting structures that we see is that layer structure. So again, going back to the system where there's no switching interactions, or if the switching interactions are very slow, you see that these particles aggregate on an area that is blue, and the blue ones in the area that is blue, and the yellow ones in a different area. If the switching is too far, this process simply just doesn't happen, or it happens at a time scale that is not fast enough to create anything, and the system just looks like a well-mixed system, where the switching happens so fast that the system just cannot find anything. But if you pick that switching rate correctly, and you balance those two processes, you can get a structure that you couldn't before. And this is spheres of concentric layers of alternating types of material. So you have blue, yellow, like that. Again, this is an example of just by switching the local rules, we have affected the bulk properties. Right? Here is a video of a little bit how the system assembles on a little bit denser system, where you can see the system trying to phase separate, but these new areas are building in together until they stabilize these patterns of spheres within spheres within spheres, and new spheres being born all the time. If you perturb it, like in this case, like here at the end, when the system is already built, if you perturb it a little bit, the system goes back to this steady state state, where you can have very resilient states.
How did you perturb the system?
You can just apply any shear. You can change the switching rate to a different rate, and do other changes.
How this pattern is depending on the probability of the switch.
Oh, I'll talk about that in a minute. But that's another point of this of this. I'll get to this in just a minute. So here is just a graph showing the RDF, that is kind of like the probability of finding another particle within a certain distance from a particle. So the red one is how likely a blue particle or a particle is likely to find another particle of the same type, and the yellow one is a particle of the opposite type. So here we can see that as the time goes through, when there is no switching, particles of the same type are grouping together, particles of the opposite type are getting farther and farther away. Right? And then when there is switching, these ones are getting together, but the switching is forcing this new interface in the particles. Again, before we could only see them getting farther away. Here we see them getting farther away, but we're forcing this inner layer from within them. And what is happening is, like the way that this system are evolving, is that particles are coming together. They're forming, they're phase separating like normal, and they're making aggregates. As the aggregate grows, particles within them are switching to the opposite type, and they're trying to diffuse to the edge, and then go around and find another group of particles, another aggregate that they like to be with. As these aggregates get bigger and bigger, other particles start switching, and they have a probability of finding themselves together and nucleating a new layer. once this layer is nucleated, other particles that switch will be likely to join that nucleus and start sealing that new layer. Particles are joining the outside, coarsening the size of the aggregate, and some of the particles are also leaving the aggregate. And then particles or aggregates with the surface of similar types, they come into contact, they share material, and there's a transfer of material between different aggregates. Between these four processes, they stabilize an actual size of an aggregate and the size of the layer. Here we can see a phase diagram of this system. So if the switching is too slow, like in this case, we can see that here we get the phase separated system. It is able to go back to this equilibrium configuration. At a sweet spot, we can get the layer structure, and if it's too fast, the system goes back to well mixed. And also in this phase diagram, we can see the two dynamics that are important in our system. We can see the probability, the switching probability, that is governing how fast you are switching these particles from one type to another, and the friction coefficient, that is governing how fast these particles are able to diffuse through those clusters to join the system. Within this region of switching, the layer size changes as you increase as you change the switching probability. So before, like on the phase separated region, if you have the material, you start switching, no layers occur. You reach a critical point when you start seeing the layers, and by controlling this outside parameter of how fast these particles are going to switch, you can tune how thick and how many layers these systems are going to have. After, if you switch it too fast, again you go back to a mixed system. But now you have a material whose properties, if they depend on these layers, mind that the layers give rise to the optical properties or some mechanical properties of the system, you can dynamically turn the properties. But by this external control of how fast they are switching, how fast the perturbation is, and without having to change the temperature, without having to change any other thermodynamic parameters on the system. So you have a system whose structure can be dynamically controlled by an outside source. Again, here we have the labels didn't come out right, but this is the potential energy of the system, and we can see that the system has been captured basically at a higher potential energy. And as you switch this, you change the switching rate, you can capture it at multiple different potential energies. So the faster that you switch, the more interface that you can stabilize, until the point that it doesn't matter, like it reaches the equilibrium configuration. Here is the amount of energy that is dissipating into the environment, just like a verification to make sure that the system that you're simulating is a real system, something that could be done experimentally.
One of the things you see is that instead of forming one big droplet, you form several droplets that are roughly of the same size.
Yes.
Is it something that comes from your parameters, the size of this? Can you tell what the size of this cluster will be?
So,
they look like they have kind of similar sizes, right?
Yes, they are of similar sizes. Again, they are limited by the fact that if they touch another cluster, one of them will shrink and the other one will grow. Okay. And if it's large enough, it will start sustaining new clusters inside them, and if it grows large enough, it will start breaking apart into smaller clusters because of the particle switching up. So the breaking apart and the coming together and coarsening can stabilizes a certain cluster size. We haven't really looked at how the total cluster size scales as a function of the parameters, but we do see that there is a terminal size. So if you make the system twice as big, the clusters remain the same size at the end. You just have, twice as many clusters. The second system is a little bit different. So it's still a set of particles. Again, these building blocks that we're engineering, but we only have one kind. And these particles have an interaction between them that can be attractive or repulsive. So you can turn them on and off, basically. So when there are nanoparticles with a surfactant attached to them, that you can turn that surfactant by shining a light between hydrophilic and hydrophobic. Right? So when they're in one configuration, they don't want to come together, like in this case, in the off time, and then they just diffuse through the system. When you switch the light on, you can turn the interactions on, and then they come and aggregate together. And this is a reversible process. By switching the right wavelength of light, you can switch them on and off, repeatedly. Again, this is another system that we understand well how it aggregates. We see the aggregation of particles. If you leave the system, all the particles are going to end up coming together. By adding this disaggregation time, we can distort the system. We can control how the system aggregates using an external control, in this case the light, and change how it aggregates. This is a graph from the original paper when this was published, and you can see the silver line is the system aggregating on its own, and the other lines are at different ratios of aggregation time and disaggregation time. So here you can see that some of the systems aggregate to a certain point and then disaggregate completely and they go back and forth, kind of an interesting behavior. And other systems actually aggregate faster by switching them on and off. And some of them reach a similar aggregate size. If we run the system a lot longer, what we result is with a system where the aggregate size, or a range of the aggregate size, is captured. Now imagine that you have this material, and you just let it run. Particles are going to continue aggregating, and reach as big of aggregate as they can. If you're continuously switching them on and off, they're going to try to aggregate, and then at some point, the disaggregation time and the aggregation time are going to be balanced, and you're going to establish basically a range of valid cluster sizes. If you put this into a real material, optical properties of materials usually depend on aggregate sizes. So if you have an aggregate of some number of particles of some size, you're going to absorb or be opaque to a certain wavelength of light. If you change that size, it's going to affect a different wavelength. In this case, if you had a material and you just let it aggregate, the only wavelength that you're going to be able to affect on the long term is the one that is determined by the whole system aggregating together. With this, you could envision a material that you can control the aggregate size, so you can control the wavelength that it is being affected with an external parameter that you switch it on and off. So you have a material that if you switch those two lights or two control signals on and off at a certain ratio, is opaque to red. You change that material, even though it's already been made, it's a material that is sitting, you don't change the density, you don't change the temperature, the only thing that you change is that external controlling parameter, and you shift it to yellow, or you shift it to a different color, and you can do this dynamically to move from one color to another by just shifting this external parameter. And this could be extended to other properties of the system, and have materials that shift their mechanical properties, that they become harder or more, or again, change their properties as a response of an external parameter that you have introduced to them. So in this system, we have, or in these two systems, we have systems that are very fairly understood. The first one is the system that phase separates through spinol decomposition, kind of like oil and water. In the second one, a system that aggregates. And we've thrown a little change, a little temporal dependency onto that system, and have been able to capture a state that was not available before. On the first one, we were able to make a structure that is not possible without this with the original building block. On the second one, we have captured a phase or a state that is a transient state that is not stable on the original material. By doing like small changes on how the building block functions, on how the building block works. So, just I guess one thing to just, if you're going to keep something from this talk, is that as you build your systems and then study things that you understand, kind of think about things that you could, like that little wrench that you can throw onto the machinery that you already understand, that you could do to capture things that are not possible before. Either to create new things or to stabilize things that were not possible with the current systems. Any questions?
So what happens if you carry out these simulations in 1 or 2 dimensions? So instead of clustering in 3 dimensions, they only have 2 degrees of autonomy. Do you know what the dynamics are there?
I've run simulations into the systems. You see this. It's kind of it's basically rings within rings of systems. But on that case, it's a little harder because if you run the system to dilute, it's hard to get just aggregates that are not kinetically trapped. If the system is really packed, these rings are coming into contact the whole time. So, if you just later, I can actually send you some videos of the system that I run. But they look kind of like almost like cells within, like with one wall and then different rings inside them, and then they're always touching and merging into each other and moving around. So
there's no stable state in the
no, the length scales are stable. The number of aggregates is stable. The actual configuration of how those stables, those rings and patterns are distributed are not. So there is again like a stable length scale, but not a stable pattern itself. It's not frozen. It's always moving.
Okay.
Mm-hmm.
So I might push that too much from what you're actually referring here, but one of the interesting things that we do in the complex system is by mixing different backgrounds and different ideas. And it's fun to see how people model, for instance, people and their opinions as a spin model of like, if you are left wing, you are like spin up, you are right wing, you have a spin down, and people model actually what happens in a system that you have all those people interacting with each other, and of course, what you see in the end is this polarization of left and right. And if you take Scott's class in complex systems, is one of the things we see. So I was kind of going further and applying the same things that we're finding here to imagine that you have the same population now, but people can change their opinion. And what you would see is that if they change their opinion in some kind of rate that is fast enough, they would actually not phase separate. They would have a region of people who would be kind of an island in the middle of people that are completely opposite opinion of themselves, but they would still be stable there because people are changing opinion, they're grouping together. So it was crazy to discover that people, the crude approximation that people make to simulate some behavior of opinion behavior as a spin model, this will be interesting to see. I have no idea. Do you know anything about that? The way that people model in social sciences, scale model for.
Yeah, I mean, we have Patrick Grimm's group. Patrick Grimm's a philosopher over at Stanford, but we do a lot of that stuff.
Right. Yeah, I was imagining whether, I don't know.
No, so that's my question about the 2D is that Bob Axelrod has a canonical model on culture dissemination. And so many of the properties here that occur in 3D seem to be extensions of what occurs in Axelrod's model in 2D. Though your results in 2D seem to diverge from his. And so I actually kind of want to know, I mean, like, this is offline. I'd be interested to understand why the dynamics that you see are different from those in his model. But yeah, there's a lot of overlap with when you just have very simple rules of agents trying to seek out other agents and repel dissimilar agents. Like these are kind of classic models when we think about culture. So Schelling's segregation model is another canonical model where we say that all agents want to do is be with like agents, and we also get segregations. I've never seen a model that gets such great geometric regularity. So Axelrod's model does get small, kind of pulled out, culturally distinct clusters, but they're not nearly as elegantly laid out. And so I just like.
But also other things, like they change their properties, or the set of rules is the same from the beginning.
The set of rules is the same from the beginning, but there's much more stability in the end, unless you perturb.
Yeah, and they're very, like, in the structure in this case, you have to be very careful with simulating, especially the systems that are far away from equilibrium. When you're introducing energy into the system, like that could be changing the speed at which your particles segregate, and making sure that you address for it properly. In previous studies, where for example, Monte Carlo has been done, where you to be sampling over different configurations on equilibrium, you get like stripes, and like over the last few years, we figured out that that's really not the right result, and the reason is because you are not addressing for how the correct dynamics of how the system segregates.
So what is it about the initial conditions or the energy in the system that produces different geometries? So you said that in some configurations you get stripes, and in others you get these spheres encompassing spheres.
No, the simulations are using different methods.
So what are those different methods?
So one of them is Monte Carlo, that is stochastics, and in your sampling the configuration space of equilibrium configuration, where you're just looking at how basically like an icing model with the switching included.
Take a particle here disappears and goes randomly to another position.
Oh,
if this other position is more stable than before, you accept this. But in what he's doing, the particles are moving locally according to forces of the other particles. So there is no non-local moves.
Got it. Okay. So that's much more interesting from from where I'm coming from, which is like the cultural or political standpoint.
What, the non-local or the local?
Local, because you write very rarely do you have non-local.
You have an area of influence that you can influence your neighbors.
Yeah.
In Monte Carlo, you are literally jumping from one place to the other and accepting if one of the yellow particles in the middle of the blue bubble jumps to a bunch of yellow particles, it's going to feel better, so it's going to move like that. But if you're doing a molecular dynamics.
Here you see a lot of collective moves, like basically in your case, a lot of people coming together and then finding other people as a group. In Monte Carlo, those individual moves do not really describe the dynamics of how the system, how this idea in your case propagates through the whole population. Here we can see how like that changing in there, and then two people coming together or two particles coming together can be stable, and as more people come together, they can move together as a group. Versus in Monte Carlo, just kind of jumping from one place to another, and so we get different results. Yes.
So on the phase diagram for your first system, this is, I guess, a little lower level that I thought was kind of interesting. I was wondering, so right around in between like 10 to the minus 7 and 10 to the minus 5, you have this sort of, in the second row up, you have this sort of, can you really just tune the switching probability, start in one phase, get into another phase, and then get back into the first phase?
No. I mean, I put this line is kind of like as idea. This is not a re-entry point. This is just basically at those border lines. It's kind of fuzzy. So the algorithm that I this is an artifact of the way that I've calculated which phase is it on. It's not really like, but it was a result. So I might just need to do a larger sample size to actually get rid of that. But that's not a re-entry point now.
Okay.
So in 2 weeks, I don't know if you guys received an email, Professor